Hello and welcome to Pep Talk with me, Mr. Pepperell. In this episode we're going to find out what happens to the nucleus of an atom when it undergoes a nuclear reaction. So, by the end of this video you should be able to tell me how does the nucleus of an atom change when it emits an alpha or beta particle, and how can we actually represent the emission of an alpha or beta particle from the nucleus of an atom. Now you'll notice there that that second objective has got a little H after it. That means it's something you definitely need for the higher paper if you're hoping to get more than a C at GCSE, which we are.
So we know that both alpha and beta particles are going to be emitted by a radioactive or unstable nucleus, but what actually happens to that nucleus when that particle has been emitted? Okay, so we're going to take them one at a time, and first of all we're going to think about alpha. So when an unstable nucleus emits an alpha particle like this one here, it has a big impact on that nucleus. Both its mass number and its atomic number go down because it's lost 2 protons, thereby affecting its atomic number, and it's lost 2 protons and 2 neutrons, thereby affecting its mass number. So to find out how this actually affects the nucleus, I think it's best to use an example, and the example we're going to use is this isotope of the radioactive element uranium called uranium-235. Okay, and uranium-235, we can see there, has got a relative mass of 235 and it's got an atomic number of 92. So due to its unstable nature, uranium emits an alpha particle. Okay, now the element was uranium as it had 92 protons, but now it's lost 2 of those protons. It's not uranium anymore, it's actually something different. In fact, what's happened is our uranium has decayed into thorium. So an element with 90 protons is thorium. We can also see that the mass number has gone down by 4 because it's also lost 2 neutrons. It's lost 2 neutrons, 2 protons, so we can see here that the relative mass has decreased by 4 to 231. And what we can see is that this decay event is just actually a balanced equation. If we have a little look over here, we can see that what we've got is just like you would balance a chemical equation. It works in exactly the same way. Okay, we've got 235 here as our relative mass number, where the decay event has taken place, so we've got 231 there as our relative mass number of our new element that our uranium's decayed into. Well, where's that 4 gone? Well, 4 is the relative mass of our alpha particle that we've lost. Okay, uranium, the atomic number was 92. Decay's taken place. We've now got a new element with a atomic number of 90. Where's the 2 difference gone? It's the number of protons in our alpha particle. So it's just like balancing an equation basically. We can see here that 231 plus 4 gives us our 235, and our 90 plus our 2 gives us our 92 over there. And in fact this is just called a nuclear decay equation. So let's try another decay equation just to see that you've got the gist of this. Okay, so it says here, complete the equation for alpha decay of thorium. So this radioactive isotope that I've got here is going to lose an alpha particle. Write out the equation for me. Pause the video, have a go, then restart and see if you've got it right. So hopefully you've paused this, you've had a little go, you've got something written down. Let's see if we've got the same thing written down. Our thorium is going to lose an alpha particle. Well, the relative mass of an alpha particle is 4. So this number here is going to decrease by 4. Let's have a look if that happens. Yeah, what's happened is our thorium has decayed into radium. We've lost 4 from our relative mass number down to 224 there. And of course we've lost 2 protons as well. So the thorium has turned into radium with 88 protons, and of course just to balance that out we need the alpha particle there, so we can see that that is our balanced decay equation there. Okay, so that is alpha decay, and it's the same principle, just a different process for beta decay that we're going to look at now. Okay, and you'll recall that a beta particle is a electron that we've got here that's emitted at high speed from an unstable nucleus. Well, hang on, you might be thinking to yourself, there aren't any electrons in the atomic nucleus, and you're right to think that, but in the case of radioactive isotopes they can actually be created When the nucleus has got too many neutrons, what can happen is a neutron can actually change into a proton, and when it does this, an electron is also formed and immediately emitted at high speed, and that is our beta particle. So the beta particle is not made up of protons or neutrons, so it's got no relative mass. It's a high energy electron that's created when a neutron decays into a proton. So let's see how this affects the nucleus, and we'll use an example again. We're going to use an isotope of potassium, potassium 40. Okay, so in this case then, in our beta decay event, our isotope of potassium here, potassium 40, relative mass of 40, number of protons 19, is going to decay into an isotope of calcium. So have a look at those little numbers there a minute. Think about what's going on. We've got a relative mass of 40 here, but a relative mass of 40 here, even though a particle's been given out. And we've got a atomic number, a number of protons, 19. Over here, the number of protons has gone up somehow. So how can that be? Well, think about what I said. What happens is one of the neutrons that makes up this relative mass number decays and turns into a proton. Okay, so this is the number of neutrons plus protons. All that's happened is one of those neutrons has changed into a proton. So you've still got the same number of neutrons plus protons. So the relative mass has not changed at all. But what has changed is the number of protons. One of the neutrons up here has changed into a proton. So this number has gone up by 1 to 20. The change in the number of protons makes it a different element. Calcium's got 20 protons. And just to double check what's gone on there, we can see that the beta particle has been emitted. Let's have a little look. The beta particle, it's got a relative mass of 0. It balances the equation. Calcium, relative mass 40, plus 0 gives us the relative mass of 40 over there for the potassium. Calcium here, number of protons, is 20. Well, although this isn't really telling us the number of protons in a beta particle, it's not telling us it's -1 protons. It's actually the relative charge of -1. In our equation, it serves the same purpose. 20 plus -1 gives us 19. So we can see again, it's a balanced equation. Just by looking at the relative masses and the charge here, we can see exactly what's gone on in a beta decay event. So let's try an example of a beta decay equation as well, just to make sure we've got the gist of it. Our question asks us, complete the equation for a beta decay of the isotope of copper, copper 64. So to start with, we've got copper, relative mass of 64, number of protons 29, beta decay is going to take place. Pause this now, have a little go, write down what you think, use your periodic table just to check what element it might turn into when it gives out that beta particle. Pause it, have a go, and then come back. Hopefully you did pause it, hopefully you had a go, and hopefully this is what you found out. Okay, what's going to happen is beta particles being given out, so one of these neutrons changes into a proton, but that means that number stays the same. But one of the neutrons changes to a proton, which means this number, the proton number, the atomic number, is going to go up by 1. So what you should have done is found that your copper changed into zinc. Okay, zinc, the atomic number is 30, so one of these neutrons changed to a proton gives us an atomic number of 30, which is the atomic number for the element zinc. Okay, of course, one of these neutrons changed to a proton. This number is the number of neutrons plus protons, so that didn't change at all. And just to check, just to balance that all out, we can see we've got a beta particle there as well. Well, our relative mass of the beta particle is 0, so 64 plus 0 is 64 over here. Atomic number 30, number of protons 30, plus -1, which is actually the relative charge. It's the beta particle has no protons or neutrons. Okay, so -1 is the relative charge. 30 plus -1 gives us 29. So if you're thinking to yourself, well, this is a bit complicated, or this sounds a bit hard, that's because it is a bit hard. Okay, you've got to be able to do these decay equations for alpha and beta particles for the higher paper in the GCSE to get the high grades. Okay, so this is going to be the harder stuff, but it's something you're going to have to do if you want to get the top grades. Okay, now finally, you might have thought to yourself during this, we've talked about alpha, we've talked about beta, what about gamma during these decay events? What about gamma radiation? Well, here's the thing about gamma radiation. Gamma radiation is just pure energy, and it's emitted by the nucleus at the same time as alpha and beta particles for reasons I won't go into now. Okay, and as it's energy and not a particle, it has no mass, so its emission doesn't cause any change to the nucleus at all. Okay, there's the same number of protons and neutrons there before and after it's emitted, really. Okay, so gamma being given out doesn't cause any change to the nucleus.